As you know, since the 60s, we know that there are quarks inside the protons, neutrons, hadrons, etc., and that they are confined. And since then, it was considered how could we treat hadronic matter in such a way that quarks could be released from this confinement. There has been a lot of theoretical work which predicted experimental signatures for this deconfinement. And since 1994, on the basis of all this theoretical work, and a broad experimental program was launched at CERN. It was broad because of the diversity of the signatures which were expected and the difficulty of addressing all of them in a single experiment. We have been working with the SPS here with ions of increasing mass, and it seems appropriate now to assess the results after this long and vigorous program. To give an overall view of what has been already published here and there, in a global assessment of what has been accomplished. It is appropriate since, as you know, we are in the process of completing that program with available tools at CERN today, and that we owe to the scientific community a broad, detailed, educated, I would say, information on the results obtained. It is also appropriate because, as you know, tools with even higher potential than those available at the SPS will be soon underway to proceed further in the study of deconfinement of quarks. Of course, I'm thinking of RHIC, the relativistic heavy ion collider in Brookhaven, which is starting now its campaign of a dedicated program with a dedicated machine, and also of all the work which is already being accomplished in the member states of CERN and at CERN itself to build ALICE for use with the LHC from 2005 on. So it appeared to all of us that it was an appropriate time to make an assessment and to try to put together all the information received. This is the goal of this morning, for which you have seen the program. What you might not have seen the program, that there will be a coffee break in the middle. And I will call immediately on Ulrich Heinz, who will talk about making quark-gluon matter in relativistic nuclear collisions.
Okay, danke. Quantum chromodynamics predicts that when you compress hadronic matter to energy densities above about 1 GeV per cubic Fermi, that you make a transition from a state where quarks and gluons are confined inside hadrons into a color deconfined state, which is called the quark-gluon plasma. And you can do that either at zero net baryon density as in the early universe if you exceed the critical temperature of about 170 MeV, or you can do it in cold nuclear matter like in neutron stars if you exceed the baryon density by a factor of 3 to 10. What's known about this phase transition is essentially, comes essentially from lattice QCD calculations at the at this corner here, and from models in the rest of the domain. There's also some recent development here at very high densities that I will not go into today. The lattice QCD results for for QCD with dynamical quarks are now beginning to yield converging results. And in particular, the value for the critical temperature has now come settled around 170 MeV. The systematic errors are not something that I am an expert on and can reliably assess, but looking at how things happen, they come down every day, and they are now in the 10 MeV region or so. When you look at this diagram, you realize that this corresponds to a critical energy density of about 600 MeV per cubic Fermi, about 4 times the energy density in cold nuclear matter. But if you want to heat the system only about 30% in temperature above the critical temperature, you already require something like 3 to 3.5 GeV per cubic Fermi. So there is a very steep dependence of the energy density in the neighborhood of the phase transition, as of course expected, and it's important to keep these numbers in mind. At this phase transition, 2 things happen simultaneously. One is the deconfinement of colored constituents. The other is chiral symmetry restoration. And it has been shown in lattice calculations that the response functions corresponding to these 2 types of phenomena show peaks at exactly the same point, irrespective of what finite quark mass you use in the simulation, and there is no indication that this changes as you go to the physical limit of nearly massless quarks. So given this background, the first interesting question is, of course, what is the energy density that we can reach in lead-lead collisions at the SPS? There are several ways of estimating that. The simplest one is using the formula provided by Björkén in 1983, which assumes energy conservation combined with the hypothesis that along the beam direction we have scaling expansion of the system. And if you take this formula and insert the overlap area for 2 lead nuclei colliding at 0 impact parameter, and you evaluate this at the time of about 1 Fermi over C after impact, because that is the typical time for secondary particles to form, and you insert the measured value for the transverse energy produced in these collisions, which is 400 GeV per unit of rapidity in central lead-lead collisions, with even about 10% more if you go to very, very central collisions. Then you end up with an estimate for the energy density about 1 Fermi over C after impact, which is somewhere between 3 and 3.5 GeV per cubic Fermi. More sophisticated analyses can be done by analyzing the final state of the collision by methods that will partly be discussed later, and then back extrapolating in time to the initial state, and you come up with very similar values. I think it's important to point out that you can get that you get similar energy densities even if you refuse to believe in quark and gluon degrees of freedom as the relevant degrees of freedom at the beginning of the collision. Here is one simulation of a class of models that use strings and string fragmentation to predict what happens in nuclear collisions. These models are tuned to observations in proton-proton and proton-nucleus collisions, so they are highly constrained, and they are also driven to energy densities between, say, 2 and 10 GeV per cubic Fermi in the very few instances of the collision. And it also shows you that the strings or other types of pre-hadronic degrees of freedom actually dominate the expansion dynamics for quite some time, until then finally hadrons appear and dominate the expansion at the later stages. So much about the limit of the initial stage. What about the final state? To make things short, the final state, when you analyze it, gives you a picture of a thermalized system, a system in thermal equilibrium, which explodes rather violently, an exploding thermal fireball. And you will see later in this seminar experimental spectra which show that all the hadrons show very nice thermal spectra. The effect of the collective expansion shows up in a blue shift of the slope, according to these types of formula. And what's interesting about it is that the flow affects particles with different masses in the non-relativistic region differently, leading to different types of slopes there. And you can use that mass dependence of the effective slope to try to separate the thermal from the collective motion. Another another observable where the collective flow shows up very prominently is in the transverse mass dependence of two-particle Bose-Einstein correlations called HBT, Hanbury-Brown twist correlations, and in the transverse mass dependence of deuteron coalescence probabilities. So these are Bose-Einstein correlation data, these are deuteron coalescence data, and they also show a significant transverse mass dependence which is ascribed to the expansion flow. The most accurate way of extracting the flow and separating it from the thermal component is by combining these two types of information. And what one then finds is that the last interactions in these collisions among the hadrons, the last strong interactions, happen at a state where the system has cooled down to about 100 MeV and expands very violently with more than half the velocity of light. At that point, the energy density has decreased to something like about 50 MeV per cubic Fermi. So, big question is, of course, what happened in between? What happened when while the system was going from the initial high energy density to the final low energy density? And in particular, what can we learn about the behavior of matter in the very dense initial stages? At this point, I would like to summarize a few of the key predictions that were made before this experimental program started about how a quark-gluon plasma should manifest itself in the data. The first of these predictions is the prediction of strangeness enhancement and the approach to chemical equilibrium between up-down and strange quarks in heavy ion collisions. And the mechanism for that is supposed to be a shorter time scale for the production of strange quarks and strange antiquark pairs by gluon fusion. And this is a direct consequence of the gluon deconfinement in the quark-gluon plasma, which leads to high gluon densities, and chiral symmetry restoration, which makes the mass threshold for the strange quarks in the final state small. There is, of course, a hadronic background that one can conceive here, which is the normal production of strangeness through associated production, followed subsequently by strangeness exchange. However, it was shown by detailed calculations and simulations that particles which contain more than 1 unit of strangeness and which are typically very heavy, hadrons which contain more than 1 unit of strangeness and are typically very heavy, in particular when they are antibaryons with more than 1 unit of strangeness, that their production is inhibited by the low antibaryon densities and high mass thresholds, and the corresponding equation times are just very, very long. So maybe I can put this on the other side. Sorry, Lou. While I look at the strangeness data, there are three key observations that I've summarized on this transparency. First, when one analyzes the final hadronic abundances, they indeed correspond very nicely to a state of chemical equilibrium. What's shown here is an analysis published in Physics Letters by Braun-Wunsinger, Hepper, and Stachel, which compares predictions from thermal and chemical equilibrium model as lines and the actual data for something like 18 different particle ratios. And over several orders of magnitudes, everything fits rather nicely. The corresponding temperature that one would extract from this analysis would be a chemical equilibrium temperature of about 168 MeV, which coincides with the predicted phase transition temperature where the quarks should rehadronize into hadrons. It has been shown by simulations and by rate calculations that there is no time during the short time of the collision that the hadrons could establish such a kind of chemical equilibrium by hadronic inelastic scattering. So this implies that this apparent chemical equilibrium must have been pre-established at the point of hadron formation. It's not a hadronic rescattering equilibrium, it's some kind of pre-established equilibrium. And the simplest and I think most consistent interpretation of this is that you have reached the state by a statistical process by which the hadrons appear from other degrees of freedom, from the quark and gluon degrees of freedom, by a statistical hadronization process. The second key observation is that this apparent chemical equilibrium comes along with enhancement of strangeness overall. If one calculates from the final state the fraction of produced strange anti-strange quark pairs compared to the produced light quark anti-quark pairs, this ratio is different by a factor of 2 from elementary particle collisions, proton-proton, electron-positron, proton-antiproton collisions. And this indicates that there must be a new type of rapid strangeness-producing processes which are active before the hadronization, before the hadron production occurs, or during the hadronization process itself. Now, when you look at how this enhanced strangeness is distributed among the strangeness-carrying particles in the final state, you find a very striking behavior, namely that those particles which contain several units of strangeness profit from this enhancement much more strongly than particles which have only 1 unit of strangeness. This again supports the interpretation that this is a statistical process which just redistributes the available strangeness according to statistical laws. And none of these 3 observations can be explained by hadronic final state interactions. In particular, you cannot understand why particles which are very, very heavy and suppressed by high mass thresholds should be enhanced by a factor 15, while other particles which are light are enhanced only by a factor of 2. The second key prediction of quark-gluon plasma is that charmonia should be suppressed. And the mechanism behind that, as advocated by Satsun Maitsui in 1986, is that the color deconfinement, the deconfinement of quarks and gluons should lead to color screening, and that this should inhibit the binding of the charm and anti-charm quark into a bound state, into a color-neutral bound state. Again, color deconfinement and the high gluon density are the 2 features of the plasma which lead to this phenomenon. And it should lead to a sequence of suppression patterns. First, the lightly bound psi prime should be screened away, then the chi-c, and finally the very strongly bound j-psi state itself. Hadronic backgrounds for this type of suppression are, of course, again final state interactions of these charmonia, either with the incoming nucleons in the 2 nuclei as they interpenetrate each other, or later on with the formed hadrons which move together with the j-psi and scatter with them. Now, here the experimental observations are shown in this and the following diagram. This is the latest from about 2 years ago, where it had been established that indeed, when you look at the yield of psi primes normalized to dimuon pairs from the Trallian process, which is understood theoretically and can be used as a normalization process, or of the j-psi, and you plot this against the variable which counts the length of the cold nuclear matter that sweeps over the charmonium as the 2 nuclei penetrate, that there is a deviation from the expected absorption on these nucleons, which sets in at about 5 Fermis of these variable for the j-psi, and at about 7.5 Fermi for the psi prime, and about 7.5 Fermis for the j-psi. So first the psi prime gets destroyed, and then j-psi gets destroyed. But now, since last year, we have much more accurate data on the j-psi suppression itself from lead-lead collisions. Here now plotted directly against the measurable variable of transverse energy, which is a measure for the centrality of the collision. And you see that the suppression of the j-psi happens with an interesting shape in the ET dependence. And there is a first suppression by about 40%, which can be tentatively assigned, although it's not directly confirmed, can be tentatively assigned to the suppression of the 30 to 40% chi-c contribution to the j-psi, which makes radiative decays into j-psi. And then perhaps in the very most central lead-lead collisions, the j-psi ground state suffers additional suppression. Now here, again, of course, you can try to simulate this by hadronic final state interactions. And let me just put up here 2, I'm stealing now the transparencies from Chicalo from last quark matter conference. 2 of the typical type of kinetic simulations which use hadronic degrees of freedom and try to understand chip size suppression by final state rescattering with the hadrons. And you see that the shape is different from what is measured, and also all of these calculations, and that's a generic feature of all kinds of co-mover scattering models, saturate at high, at small impact parameters, at high ETs, and cannot reproduce this enhanced degrees at very central collisions. So finally, after having discussed these two phenomena, and perhaps one should stress at this point that these two observations, although they are consistent with the expectations from quark-gluon plasma, they suffer, of course, intellectually from the problem that we are discussing observables that have undergone a lot of rescattering, of hadronic rescattering, after the interesting initial stage that we are trying to extract from there. And so we are arguing that the final state still has the memory about the initial stage, but there is this intermediate rescattering stage which makes you feel perhaps a little bit uneasy. The most direct way of looking at the quark-gluon plasma would be looking by electromagnetic radiation, because electromagnetic radiation does not rescatter, it comes out immediately, and it gives you direct information about the structure functions, the momentum distributions of the quarks and perhaps the gluons in the quark-gluon plasma. Unfortunately, these signals suffer from huge experimental backgrounds, like Trellian open charm decays, Bremsstrahlung contribution from charged hadrons, and for the photons in particular, you have the decays of the neutral pions and etas in the final state, and there are lots and lots of those. And that makes the extraction of a direct signal from all these background experimentally very difficult. There are some intriguing indications for a direct contribution in lead-lead collisions, both in the dileptons and the thermal photons, but they are marginal, and their relation to the predicted thermal radiation is not clear. This is a point where we expect dramatic progress when you go to RIC and also to LHC, because the thermal radiation rate grows like the fourth power of the temperature, and we'll be able to reach higher temperatures, significantly higher temperatures at the higher energy densities. So if I take all of these observations together, it suggests a very simple picture for these collisions. You start out with an initial energy density of about 3 GeV per cubic Fermi. And although we don't have really direct observational evidence that already at that stage the system reaches a state of thermal equilibrium, if it would do so, it would start here at around 210 MeV. Then some kind of physics happens here, which may not happen in this phase diagram if it's not completely equilibrated, which brings the system to the hadronization point. And during this stage, we have the shape size suppression and we have the strangeness enhancement. As the quarks and gluons hadronize and form their hadrons, we establish a system in chemical equilibrium by a statistical hadronization process, which gives a snapshot of the phase transition temperature of 170 MeV. After that, a lot of elastic scattering is still going on, which cools the momentum spectra of the particles down without changing their chemical composition. At about 100 MeV, the system stops interacting completely, the momentum spectra are frozen out, and they show the thermal behavior with a boost, with a blue shift corresponding to the velocity of light. So let me summarize. And the summary will be in 2 steps. First, the positive side. I think we can safely say that we have created a new state of matter at about 20 times the energy density of cold nuclear matter, which behaves collectively and leads to a gigantic explosion of the collision fireball with about half the velocity of light. So we have recreated Big Bang's little brother in the laboratory. This state exhibits features which cannot be understood in terms of conventional hadronic interactions. These are the chemical equilibration, the strangeness enhancement, and the shape size suppression. These 3 phenomena require strong interactions with large inelastic cross-sections in a state of high energy density above the critical value for deconfinement. And they are consistent, at least, with the expectations from a plasma of deconfined quarks and gluons. And the hadron abundances appear to provide a snapshot of the predicted quark-hadron phase transition at about 170 MeV. In analogy to the Big Bang, I call this primordial hadrosynthesis at the phase transition. And these observations taken together, I think there is no question that this constitutes a quantum jump in our understanding of dense matter at extreme temperatures and energy densities, and it testifies to a great success of the CERN heavy ion program. However, if you ask yourself whether all this intriguing evidence taken together can be really taken as proof that we made, as proof beyond any reasonable doubt that we made quark-gluon plasma, then I think the honest answer has to be no. There are still missing pieces in the game. I think on the theoretical side, what is really missing is a complete and consistent and fully dynamical theory of heavy ion collisions, which does include quark-gluon degrees of freedom explicitly and includes a reasonable model for the quark-hadron transition and is able to explain all the data. I don't say that this doesn't work, it's just that this theory does not exist, and it's actually very difficult at the SPS because, as I showed in the beginning, we are always near the phase transition where everything is very difficult, non-perturbative, and so on, and this may become easier when you go to RIC and LHC, where QCD becomes a little bit more perturbative. And the other big thing is that we have to continue trying to eliminate other I said conventional hadronic dynamics is not able to explain the data, but there may be other non-conventional mechanisms which are not identical to quark-gluon plasma, like color ropes, baryon junctions, and so on, which have to be eliminated. And that requires a systematic test of model against experiments in PP, PA, and AA collisions. And I must say, unfortunately, the database for this part is highly incomplete, and the SPS could actually provide more information here. On the experimental side, I think what is clearly needed is once we have convinced ourselves that there is a hint of quark-gluon plasma, we should try to find out where is the energy threshold for it. Where is the energy threshold for quark deconfinement? That could be done at the SPS. It requires measuring an excitation function of various observables. What is the system size threshold for achieving collective behavior in such nuclear systems? How big does the system have to be to establish chemical and thermal equilibration? Again, this is something that can be done at the existing energies. And I think it would be very nice to have a model-independent normalization of the JPSI by measuring not only hidden charm but also open charm. That can also be done at the SPS. What cannot be done at the SPS is probably not be done at the SPS, is a measurement of the QGP structure functions by direct electromagnetic radiation. For that, you really need the higher energy densities provided by RIC and LHC. And also, the much longer time scales, lifetimes for the plasma that this then entails, will enable you to probe the quark-gluon plasma in great detail by various kinds of hard probes, jets, which can be get quenched or can that you have ecoplanarity between jets, open purity, epsilon spectroscopy, and so on. And so, although one can make a reasonable argument that since we have now scratched the surface, we should really work hard at the SPS to get as much additional information as we can get, and I'm sure these discussions will go on very rigorously in the weeks to come here. I think there is no question that eventually, in order to complete this picture and to provide a full characterization of the quark-gluon plasma, we need RIC LHC, and therefore we are all looking very much forward to the first beams at RIC, which are supposed to come in a couple of months.
The lighter quark which is not in the valence
In a sense, the Strangeness enhancement is a consequence of such a mechanism. If you go into chemical equilibrium and you have filled up these Fermi levels for up and down quarks, it becomes easier to occupy a third Fermi level for strange quarks. So this is what drives the system towards a higher level. But the interesting fact is that this happens so quickly, and for that I think you need some new mechanism which is not usual hadronic physics, like something that goes faster than usual and can happen in the short lifetime of a heavy ion collision.
No other question? Thank you, Ulrich. And we will move now to a presentation of the various experimental
Move out of the way, yes.
for these results. And I will first call on Louis Duberg to speak on the Gibbs suppression pattern. You've heard a little about it, which is observed the death collision ions.
Thank you.
State of matter.
Thank you.
So indeed, I am supposed to summarize here the work in 20 minutes, the work that we have done in the past 15 years. So you see the compression rate of information, which is appropriate to create, of course, quark-gluon plasma. Okay, I can point on the transparency itself. So I'm going to summarize here what we have learned about the Gibbs suppression pattern in lead-lead collisions, and this will be based on the results of experiment NA50 together with results of experiments NA38 and NA51. I will try to recall you the experiment motivation. We were biased, of course, doing this sort of research. The specific features of this Gibbs signature have been just summarized by Ulrich Heinz, and then I will try to summarize step by step how we have reached the present understanding of the Gibbs suppression pattern. So the theoretical bias of this search, this specific signature search, is that it is believed that Gibbs is produced at the very early stages of the nucleus-nucleus collision. It is believed that it retains the information throughout the subsequent evolution of the collision, and that it can be considered as an external probe because it is created in some sense by primary parton collisions before even the existence of any medium, so that it gets then embedded into the created medium, and if influenced by the surrounding, can keep memory of it and then go directly through the dimuon decay almost undistorted to the experimental detector. It is also believed that quarkonia dissociation is only possible, Ulrich explained it in more detail, by color screening or hard-gluon interaction, although more conventional interactions with plain nucleons from the target and the projectile have to be taken into account. All this resulted from the original paper written in 86, published in 86 by Helmut Zatz and Matsui, who claimed that Gibbs suppression in nuclear structure, in nuclear collisions, should provide an unambiguous signature of quark-gluon plasma formation. Since then, of course, many more sophisticated calculations and descriptions of the mechanisms have been done and published, and we know today much more than we knew in 1986. Let me summarize very briefly some features of the experimental strategy that we have constantly applied in this search. We established a solid baseline with incident protons and light ion-induced reactions. We look for any abnormal thing with similarly detected events, electromagnetic processes in fact, which are expected to be insensitive to color deconfinement as Drellian, but we experimentally check that they behave normally. And finally, we explore the widest possible range in centrality in order to detect, if any, the onset of the thermonium melting. So I'm not going to describe you the apparatus, nor the analysis techniques. Let me just say that we detect muon pairs, and for each event, we also estimate the centrality of the collision thanks to calorimeters that measure the transverse energy or the very forward energy produced in the reaction. So that we end up with an invariant dimuon mass distribution, this is a typical example, which is made of several components, the J psi peak here, the psi prime shoulder, the pure Drellian continuum, the muon pairs arising from DD bar produced semileptonic decays, and last but not the least, the combinatorial background here, which arises from pi and k decays. And I ask you just to believe me that we know how to treat the background, and we know how to disentangle the different components of the spectrum and to estimate the cross-section of the different mechanisms that are involved. So, we first started for many years with proton-induced. We are still studying proton-induced and light ion-induced reactions. We studied this at different energies, at 450 GeV incident energy and also at 200 GeV. These are all renormalized at 200 GeV. We plot here the J-psi cross-section, what we call per nucleon-nucleon collisions, divided by the product of the atomic mass numbers of the target and the projectile, which is proportional to the number of the elementary collisions, and we plot it as a function of the product A times B. And what we see is that from proton-proton up to sulfur-uranium reactions, things can be nicely parametrized as the product of A times B at a certain power alpha, and we can determine alpha like 0.92 plus or minus 0.01. This is not very new because the study of J-psi production, at least with proton and pion-induced reactions, has been started a long time ago before even this experiment started, and similar values had already been obtained. So this is what we consider the baseline of the behavior of J-psi production. Now, you have to, in some sense, to understand this behavior, and the understanding of this baseline is just what Ulrich Heinz recalled some minutes ago, namely that at least the CC bar pair, which is produced in the reaction, suffers collisions with the nucleons of the target and of the projectile it has to face before escaping the interacting region. And this is just the result of the destroying of the CC bar pair by the nucleons of the target and projectile. So that parametrizing this cross-section as a decreasing exponential of the number, rho L is nothing else than the number of such potential nucleons times an absorption cross-section, we can even determine the absorption cross-section of the CC bar pair, which lies between 6 and 7 millibarns. Now we have understood the baseline, and we can go to see what happens with lead-lead interactions. The same plot, the J-psi cross-section per nucleon-nucleon collision plotted for all the previous points and for lead, clearly shows that something special happens for lead-lead collisions. And the cross-section for lead-lead lies a factor significantly below the expected value expected from the baseline, namely something like 4 to 5 standard deviations below the expected value. Now we have to investigate in detail what is happening here. And for this, we must decrease the experimental errors, which here come mainly from the fact that this is absolute cross-sections, including inefficiencies of the detector, including uncertainties on the incoming flux. So all this has to be improved. We plot here the cross-section per nucleon-nucleon collisions. And we know that the Drellian mechanism is implicitly proportional to the number of elementary nucleon-nucleon collisions. So we check it, we studied the Drellian cross-section, and we plot here the measured Drellian cross-section divided by the theoretically calculated Drellian cross-section, which implicitly includes the proportionality to the elementary nucleon-nucleon collisions. And what we see is that this ratio is a constant from proton-proton up to lead-lead collisions. So that nothing special happens for Drellian up to lead-lead collisions, and Drellian can be used as an estimator of the number of elementary nucleon collisions. Now we can go and look into more detail at what happens plotting now the ratio of the J-psi cross-section to the Drellian cross-section, again as a function of the, let us say, the number of nucleons from the target and projectile. And what we see is a pattern for lead-lead which significantly deviates from the normal behavior obtained from the baseline. We see that for the most peripheral lead-lead reactions, things behave more or less normally, but the departure from this behavior increases with centrality. And for the most central point, we are more than, something like 8 standard deviations below the expected value. This time, the errors have been decreased because we have a ratio of cross-section which provides cancellation of all systematic uncertainties which are the same for the two experimentally detected mechanisms. Now, of course, we want to investigate in detail what happens here, and for this we need to increase statistics and to explore things in a much higher number of bins. The easy way to increase statistics is just to increase the thickness of the target. At least we thought that before. So these are the results obtained with the 96 data sample with a thicker target, 12 millimeters instead of 7 millimeters thick target. We were allowed to, we could then plot things in 15 centrality bins. We confirm that peripheral reactions behave normally. We see that there is a significant 20% drop in the cross-section, which occurs here at a value of L of about 8 Fermi, and then the J-psi cross-section goes on decreasing with a rather unclear pattern here for the most central interactions. I did not say that all these points here, for comparison purposes, are of course rescaled to the same incident energy, because here are points collected at different energies. Here everything is plotted for 158 GeV. Now we can look directly at what happens in lead-lead as a function of the directly measured transverse energy ET with our electromagnetic calorimeter. We see again the normal behavior for the peripheral collisions, the 20% drop, and the decreasing pattern for the most central collisions with again this peculiar behavior here. Again, what we need is to decrease errors. The way to try to decrease errors, which here are induced by the relatively small sample of Drellian events, is to try to replace the Drellian directly detected events by something else. And this is done using the minimum bias events, and for which we have a significantly larger sample, and then compute the Drellian events from these minimum bias events. This is the comparison of the two methods, of what we obtain with the two methods. The black circles are the previous points I already showed you with using directly Drellian detected events, and the open circles, where the error is included but is almost not visible because smaller for some points here than the symbol, the errors now are relatively small. So that here probably we have a combination at least of statistical effects, maybe something else. And we really wanted to see what happens here. We had a hint of what happens here looking at, in a small number of bins, looking at what happens with the two samples of 95 and 96 with 7 millimeter and 12 millimeter thick targets. What we see is a nice agreement for almost everything except for the last bin, for which the 12 millimeter result is significantly above. We realized that this could be due to reinteractions within the target itself. Namely, we have simultaneous a primary and a secondary interaction. The calorimeter adds up the energy of these two interactions, and so that a peripheral event, which normally should lie somewhere here, it migrates to this central region, and because the ratio is higher here than it is here, of course, it increases the result observed for the most central reactions. So, with this hint, we decided to pay the price. The price is, of course, statistics, but we devoted the 98 run to a specific run with a much thinner target, namely a 3 millimeter thick target. And the result confirmed what we were suspecting. Namely, here you have the comparison of the three runs. The 12 millimeter, we have a nice agreement for these peripheral and semicentral bins, and for the most central bins, the 12 millimeter thick target results are significantly above the other ones, and there is a fair agreement, I would say, between the 3 millimeter and 7 millimeter target runs. So that if reinteractions, there are some remaining reinteractions, they should only marginally affect the results now in this region. Now, having this in mind, we go and apply the two methods I just showed you before to analyze this 98 data sample. The triangles correspond to results obtained with the directly detected Drell-Yan events. The squares, the open squares, correspond to the method which uses the minimum bias events. Again, we see a nice agreement now, but we see that things have dramatically changed for the most central collisions. And there is a change of curvature in the suppression pattern, which occurs at a transverse energy of about 90 GeV. A similar analysis has been made using, for estimator of the centrality, not the transverse energy, neutral transverse energy anymore, but the very forward energy measured by the 0 degree calorimeter, which essentially measures the energy of the spectator fragments, the spectator nucleons, I would say. So here you have, of course, the central collisions, which release a small amount of very forward energy in the calorimeter, and here are the peripheral collisions. And what we see is qualitatively the same pattern with the same inflection point here at a value which corresponds to the value observed in ET. Now, collecting all the most precise measurements that we have, we are led to this suppression pattern, where we have put the 96 directly measured the Drell-Yan results, the 96 with the minimum bias method, excluding the most central collisions, which we know now experimentally that they suffer from reinteractions, and the 98 minimum bias results, which are represented here by the open red squares. The plot here shows a good agreement with the baseline, a first drop here, and a second accident, at least a change in curvature here. This is what in our paper we call the stepwise suppression pattern. As already suggested by Ulrich Heinz in his talk, there are several models that have been trying to account for the observed pattern using only conventional confined matter, and 4 of them are plotted here and compared with the experimental points. They systematically undershoot in the peripheral region, they overshoot here, and of course they do not count of the relatively sharp drop seen at the transverse energy of about 40 GeV. Now, what else? We have tried to understand the observed pattern. For this, we have tried to get together again all the results obtained with light and heavy nuclei, and we plot here as a function of the energy density epsilon, the measured J-psi cross-section divided, let us say simply, by the baseline. So that now the baseline is horizontal here, normalized to 1. What we observe is the drop, already seen before, and the change of curvature and the dramatic decrease for the most central collisions. The first drop occurs at an energy density of about 2.3 GeV per Fermi cube, and the second accident at about 3 GeV per Fermi cube. And this can naturally be understood if the underlying mechanism is the melting of the Chermonius states. We know from experimentally measured values that directly produced J-psis are contaminated by J-psis coming from radiative decays of the chi, and our imperfect detector, which is blind to single gamma detection, is unable to distinguish between these 2 classes of events. So that part, about 30%, this is the measured contamination. We observe something like 20% of the drop here could be accounted for by the melting of the chi, and then the J-psi would melt at a somewhat higher energy density. So I come to my conclusions, because Claude Detrazy is telling me that time is over. J-psi production rate up to central sulfur-uranium reactions shows only ordinary nuclear absorption as measured in PA collisions. From lead-lead, we deduce that peripheral J-psi is normally absorbed by nucleons, but for semi-central collisions within an impact parameter range of 1 to Fermi at around 8 Fermi and an energy density of 2.3 GeV per Fermi cube, J-psi production rate shows a drop by about 20%. From the most recent data, we see that for very central collisions at an impact parameter of about 3.6 GeV per Fermi cube, J-psi suppression pattern exhibits an inflection point followed by a steady, steep decrease. And the last part of my conclusions is, of course, the following. Our observations clearly rule out the available conventional models which try to describe the data, which are based on hadronic confined matter. They can be understood by the successive melting of the chi and the J-psi due to the peculiarities of our detector, which is enabled to distinguish between these 2 kind of J-psi origins, so that the pattern provides evidence for a change of state of matter, which could be induced by this observed state of matter should include this chermonium melting mechanism, which is predicted at least by quark-gluon deconfinement. Thank you.
Thank you, Louis, for this very interesting account of the long, systematic and dedicated search for J-psi suppression. And if there are any questions to Louis now, I'd be glad to give the floor. As I said, it was a clear account.
Thank you.
Thank you very much. So we will now move to the second experimental presentation of the
Very well. Very well.
signatures. And Johannes Staher will speak of virtual and real photons radiated by the cooling and hadronizing fireball.
Is there a microphone?
I'm sorry.
Okay, so what I will do is report on the radiation of the fireball as it cools and hadronizes and then presumably cools some more. And this radiation comes in form of virtual and real photons. The results I will be reporting on are first the electron pairs from CERN NA45 and then some evidence on direct real photons from WA98 supported by some preliminary results from CERN again. So let me start with the first topic. The CERN experiment measures electron pairs, beam hitting a target, and then two ring imaging Cherenkov counters for electron identification, a magnetic field in between to determine the momentum, silicon drift chambers, and some tracking behind the ring imaging Cherenkov counters to have precise track parameters. Recently, the experiment was supplemented with a large time projection chamber to improve the resolution. Just to give you an idea in what environment we are living, this is a picture from the ring imaging Cherenkov counters, and you see clearly rings in here which then signify electrons going into the acceptance, and this in an environment of very many charged hadrons. We'll come to this in some more detail. An image of this you can get if you look at the silicon drift chambers, where you see, of course, all charged particles. They are cleanly separated, but clearly a very large number. This is on a 4-inch scale now. If you look at the same collision in a 10 cubic meter gas detector, this is now the TPC, the target back here, and now you see many hundreds of particles. However, the tracks are cleanly separated. Now, electron measurements are notoriously difficult. The one reason is that there's a very large background of charged particles. Once we go away from the pion Dalitz decay, there's about 5 orders of magnitude difference. These are rejected with the ring imaging Cherenkov counters. Since the threshold is rather high, 32, this rejects about 95% of all pions. The remaining ones are rejected because the rings are smaller for the same momentum. The other problem is that there's, of course, a very large number of photons, mostly coming from pion decays. This means one has to minimize the material in the detector, but even going just to 1% of a radiation length, this still leaves 3 orders of magnitude more photons. So there are sophisticated rejection mechanisms and cuts needed in the analysis to reject Dalitz and conversion background. And what you see here is, first of all, the curves are simulations of the various background contributions and how, with a sequence of cuts, which I will not explain in detail now, how these backgrounds are reduced by many orders of magnitude. The total is the black line here, and this is in fact compared to a data sample of background pairs. And you see that this is very well understood in absolute terms at about the 3% level. Now there is still background left, and you will see in a minute how much, and it is completely dominated by Dalitz decays at the present stage. This shows you the measured unlike sign pairs in pink here, and the corresponding like sign pairs, and this is of course all the combinatorial background. So there's about 9 times or 10 times more combinatorial background. However, this can be rejected by various techniques. What we have done for the published data is we have taken the geometric mean of the positive and negative like sign background. There's presently also a study using mixed event analysis to reject the background. And of course, before showing you the results, of course one is worried making such a large background rejection about the systematic error in this. And this figure should give you some confidence what accuracy we have in knowing the systematics. What is shown here is the signal, the yield. I will explain in a minute what this is, for optimized cuts. For two sets of data, 95, and then the much higher statistics, 96 data, about 45 million events. And cuts are tuned on Monte Carlo. These are the two solid points, and you see that very similar results are achieved. Cuts can also be tuned on the data, and of course then going to a poorer statistics sample, there's some danger of enhancing the signal. However, the difference even here is not very large. Now, we cannot make the cuts better. This is optimized. However, we can relax the cuts and make the rejection much worse and see what then happens. And what gives us some confidence in that we really have the right signal is that over a very large range of background to signal. Now here we have 30 times more background than signal. The observed signal is not changing. So the result we see seems to be rather robust. Now, this is what we see. In green and blue, the two sets of data from 1995 and 1996, the invariant mass spectrum of electron pairs after all these cuts and combinatorial background subtraction. You see that within errors, these two sets are consistent, and they are compared to what one would expect, and this is the solid blue line from hadronic decay contributions. And what we do for the hadronic decay contributions, these are the measured results in pp, and then scale to our expectations of what these should look like for AA. Several of the yields have been measured, in fact, and since this is all normalized to charged particles, there's a relatively small uncertainty in this. Now, comparing the data to this solid line, there's certainly a very large difference. You see that the data are just a very smoothly falling, featureless curve, which is significantly above the expectation in the mass range between about 250 MeV and the rho omega pole. So it is this enhancement that is really a new feature in heavy ion collisions. This is a proton-induced collision, and PP looks similar. There, everything is perfectly understood, and this enhancement is really a new feature in heavy ion collisions. Now, this quantifies the excess as a function of mass over the solid line I just showed you, the hadronic decay contributions, and you see it's really peaked in this intermediate mass region that is filled in by some process yet to be disclosed. Now, one can study this as a function of the centrality of the collision, and what is shown here is just the electron pair yield into the acceptance after efficiency correction for 4 different centralities. And what I also indicate in green is the integral above a mass of 200 MeV. And you see that going from semi-central to central collisions, the signal grows about a factor of 6, while the charged particle multiplicity only increases by a factor about 2.5. So the growth is much stronger than linear in multiplicity. This is broken up here now into 4 different mass bins. The first one characteristic for the remaining pion-Dalitz decay region, and there you see this is perfectly consistent with 1, so this region is understood in absolute terms. This is the eta-Dalitz decay region, and again this is 1, so we understand this. And now this is the region where we see the enhancement, and you see that in this plot where the yield relative to the charged particle yield is plotted, this grows about linearly. So this would say the axis is consistent with a quadratic scaling in multiplicity, which points to collisions in the fireball producing this yield at higher mass. Of course, statistics is running out, but it looks again if this is consistent with expectations, meaning consistent with 1. Now, we have studied this also as a function of the transverse momentum of the electron pair. And what you see here is these are transverse momenta below 500 MeV over C, and this is above. Again, compared to this hadronic expectation. And you see that by far the excess is concentrated at low pair transverse momenta. At high pair transverse momenta, it is nearly consistent with expectations from hadron decays. So the question is now, what is this? It was clear rather quickly that charm, if one uses everything that's known about charm production, cannot account for this. It would have, there would have to be some huge increase by a factor 50 or so. Now, I will show you what one can do in considering the heavy ion collision. There have been many theoretical studies, and I will explain one example of a typical study that fails, and there were at least 20 of these in the literature. People really have tried everything, and then we will come to the mechanism that works to explain the data. Now, what is new in a heavy ion collision, we have very many charged pions. There are about 1,500 pions, and of course these pions can collide, and they can, for instance, make rows that then go to electron pairs. So what has been added going from this dashed green curve, which is hadronic decays except the row, is everything that comes in via pi-pi collisions, integrated over the whole history of the system. And you see, yes, there is a very large increase in yield. However, it is dominated by the row pole, and it does not help in explaining the shape of the data at all. And there's just no way to avoid this. The only mechanism to explain the enhancement where it is in mass is to accept in medium modifications. And there's several different ways in doing this. They differ, we think, more technically and really are the same physics but done in different ways. And I will come to this in a second. The red and the purple curve allow the properties of the row to change as a function of the mass, of the temperature and the density, baryon density in the system. I will show you the changes in a second. And you see, then one can perfectly account for the data and also the fact that the enhancement is very much concentrated at low transverse momenta. So the only possible explanation of the data after 5 years or so of study is an in-medium modification of the row. Now, the row is ideal because with its short lifetime and then via its small branching into electron pairs, it is a direct messenger of the properties of mesons at high density and temperature. Rows are formed all the time, then they more or less decay immediately, and they report about the state of the system at the point when they decayed. Now, we expect changes near the phase boundary to the quark-gluon plasma due to restoration of chiral symmetry. What are these changes? There have been predictions that the mass is changing, and different theories give somewhat different results. Nearly everybody agrees that the width should be increasing, and again, quantitatively depending on the theory. Definitely, there has to be a mixing of the chiral partners. And for the row, we are in the lucky situation that the chiral partner is known. It is the A1. These chiral partners exist because the symmetry is broken. Every state splits into 2 states, but as the symmetry is restored, these have to collapse again. And with the row, we really have a way in observing this. The next step that then remains to be done, and I will show you some indication of this, is one needs to connect this to the order parameter for chiral symmetry. Now, the calculation that I just showed you and that explains the data has a rho spectral function as a function of temperature and density that looks like this. And you see that as compared to the free rho in blue, there are very drastic in medium modifications, and it is something going from this purple curve to then the next two curves over the course of the collision that fills in the electron pair spectrum in the mass range where we observe the enhancement. There are many different mixings contributing to it. This is here done in a hadronic language by just coupling the mesons to baryons and to other mesons. And in this language, indeed, if we look at the rho self-energy, you see that, for instance, there's a very significant contribution coming in from the A1. Now, this is also seen in calculations that solve QCD on the lattice. What one sees here as a function of temperature is that below Tc, the rho and the A1 are two distinct states with different mass, and then they collapse to one about degenerate state above Tc. Now, I said what is missing is still the link to the order parameter of chiral symmetry restoration, and there was some progress recently in a study by these authors where they, by just putting in one state which enables the mixing between the rho and the A1, this N star 1900, they see that as the density is increasing from nuclear matter density to twice nuclear matter density, the overlap between the spectral function and also the vector axial vector correlator becomes very large. And of course, we sample densities that go from about 5 times nuclear matter density down to about half nuclear matter density. And you see how in these calculations one can now trace out the pion decay constant, the order parameter, and clearly, although this is done in a hadronic language, this is a way to come to chiral restoration, and this is what describes the experimental data. Now, let me come to photons. What is shown here is the inclusive photon spectrum as measured by WA98. This is measured with very good statistics, of course, in the experiment, and the difficulty is now to find among the many contributions to this spectrum whether there is a source of direct photons. Now, this is the background from hadron decays. Of course, the dominant source is the pi0, but the pi0 is also measured easily in the same experiment, and this is usually not limiting the accuracy of the experiment. The quality hinges in general on the eta measurement. This is the next important contribution, however, much more difficult to measure, and I should say all the others are relatively minor, and taking their uncertainties into account does not dominate the systematic error of the measurement. Here is the eta, and you immediately see the difficulty. There is a huge combinatorial background. It is very hard to see any signal. If you take the ratio between photons from the same event and 2 photons from different events, you see a structure, and if you fit this structure and extract the yield, you have an eta measurement. Subtracting all the known sources from the spectrum, you would then be left with the real direct photon spectrum. And what is shown here is the ratio of the measured inclusive spectrum I showed you before to the number of photons one would expect from all these hadronic decays. And you see in peripheral collisions, this ratio is 1, meaning the spectrum is understood. There is no signal of direct photons, and this changes in going to central collisions. In central collisions now, above a transverse momentum of about 1.5 GeV, there really seems to be some excess. What is shown in yellow here are the systematic errors, and you see that at 2.5 GeV, they are about +6, -7.9%, dominated by the systematic error in the eta. However, there is a signal beyond this systematic error. You see statistical errors are no issue at all. There is indeed an indication from CERN that we see the same thing. This is again data inclusive photons divided by the expected hadronic sources. You see here the data points with their statistical errors, and the brackets are the systematic errors. There is some indication that there's an excess. If one integrates from 0.4 GeV out, one would say this is a 12% excess. However, the systematic error is unfortunately very large and therefore not yet significant. And so this result, I should also say, is still preliminary. Now, in WA98, one sees this excess, and one can now subtract the hadronic sources, and then the red points are the measured direct photon spectrum. The points at the lower transverse momenta are upper limits. There the signal disappears into the background, but out here beyond 2 GeV, there seems to be a signal. Now, this is compared to results from PA that have been scaled to nuclear collisions, and these are the colored points out here. And I would say this really gives some confidence in the data that at high PT, one reproduces the hard scattering that's known from PA. I show here a copy I made from an old notebook of mine thinking about the photon measurement at RIC. And these are all the PA and PP results in gamma over pi. And what one sees here is that beyond about 3 GeV, any plasma signal would be completely dominated by hard scattering. Gamma over pi of the plasma would be at most 5%. And so what one ought to see out here is really only the hard scattering. And there may be a window of opportunity at the lower transverse momenta. Now this shows, and I'm coming to an end, the data as compared to 3 different attempts to reproduce the data. The purple curve is a QCD calculation of the quark-gluon-Compton process using modern structure functions and some PT broadening because we are in a heavy ion environment. This is the purple curve, and while I would say this is not yet the last word in producing the data at high PT, it seems that there's some excess possible at the lower transverse momenta, although one should also say there's always some doubt to how low PT one should carry out, or one should follow QCD. Now, the blue points come from the other end. This is just a hadronic simulation including strings, and you see that this is surprisingly similar in this intermediate range, and the data leave some room for more. Now, doing hydrodynamics and putting in a quark phase and a hadronic phase with an initial temperature of 200 MeV also seems to be below the data. However, if one increases the initial temperature to about 250 MeV, and this is consistent with the energy densities that, for instance, Louis Kluberg needs for the shape site to melt, and also the energy densities that Uli Heinz mentioned early on, starting at 250 and going to 160, there certainly this would be a way to explain the data. Now, instead of a summary, since time is running out, let me come back to the beginning and just say in 2 sentences the electron pairs show a significant enhancement at masses between twice the pion mass and the rho mass. This enhancement demands an in-medium rho modification, and we are just understanding better and better how this modification is linked to chiral restoration. There is an observation of real photons. The results are very new, and the theoretical understanding still remains to improve. However, this seems to be a combination of hard scattering at high PT and then softer processes coming from the plasma and hadronic phase in terms of thermal radiation at intermediate PTs. Thank you.
Thank you, Johanna, for a very interesting presentation of this real photon production and also specific enhancement of direct interaction. Is there any questions from you? John?
John, in this plot that you showed comparing the data with the shifted row, was that row calculation sort of completely realistic calculation, including the evolving hadronic matter distribution, or was this the one particular value?
Yeah, let me put up the transparency you are referring to. What is done here is the rho spectral function, as shown here, is calculated for every temperature and for every density, and then the calculation traces out a path in the phase diagram that we consider realistic. Now, consider realistic means using all the input we have from hadronic freeze-out at this point at 168 MeV and a chemical potential of 200 MeV, then the following expansion in the hadronic phase, as Uli Heinz showed it. So this really follows the path to the best of our knowledge from all the hadronic observables. Now, I should say this is not completely unambiguous, and one can do this either in cascade calculations or using hydrodynamics, and this is the biggest remaining uncertainty in the calculations. There's about a 20-25% difference due to that. So what I think one should do now is, of course, one can take these calculations and immediately in the same calculation compute the real photons. And this has been done for the high mass part, for the part in mu plus, mu minus. This is again virtual, below the J psi, and there it also agrees with the data. It has not yet been compared to the WA98 data, but if this calculation applies, of course, it has to do real and virtual photons the same way.
Any other question? Yes.
In the hard photon signal, is there a chance in the future to see the recoiling system? It would be a quark or something in the hard part.
I don't know how. No.
No.
The answer appears to be no.
No.
We should.
Yes.
Can you put back this calculation, not this specific calculation of the masses of the rho and A1?
Did you get the question?
It seems on lattice MCD that the sequence of final signature restoration is that actually the rho increases rather than decreases.
Well, I mean, first of all, one has to be careful about these masses. I would not take them too literally. First of all, you see, this is a quench calculation on the lattice, and then there's always this a question of masses in temporal direction and masses in spatial direction. The other question is, what do the masses mean beyond the critical temperature? And there has been a long-ranging debate in the community, and the consensus is that eventually you just see these thermal masses, and they have nothing to do with masses of a hadron. So this growth of masses with temperature above Tc, reaching values of pi t, 2 pi t, and so on, this has been known for a long time, and these thermal masses are, well, I think the interpretation is difficult. What is important here is that the two, and the same is actually true for the scalar and the pseudoscalar, for the pion and the sigma, that the two merge at Tc. Now, what is now underway is that people try to also calculate the spectral function and see whether the spectral function, as you calculated from the lattice data, also shows this large overlap. Yeah, but the absolute value of the mass, I would not attribute too much weight to.
John? Yeah.
John?
How much can you say about the dielectron continuum above 1 GeV?
Well, in the CERS data right now, we can say very little because the data are running out of statistics. However, there is the data that Louis chose not to show today, and I'm not sure whether I have them here, and that is the continuum below the J psi down to about 2 GeV. And there seems to be this excess. It is significant. It is about a factor 2 over all known contributions. And there is a speculation, there's a possibility that this is charm. However, then charm would have to be enhanced by a factor of 3, which certainly is dramatic. There is, however, also this recent calculation by Rapp, who applies the same mechanism as to the low mass part to calculate the photon spectrum at high masses, starting from the plasma and then going to the hadronic freeze-out. And that, adding this to the normal charm and trillion, that can also account for the data.
Okay. Yes, one more question.
Just wanted to finish my question. My problem is if the rho and A1 become degenerate, and if their width increases, given the fact that they are already very broad, even in proton-proton collisions, how does this compare with the improvement of the mass resolution by adding the TPC? I mean, is it not really a matter of signal-to-background ratio and statistics more than resolution?
Yeah, let me find a figure to illustrate the question. So, this is the mass resolution that Ceres had, including the 96.1, and we have added the TPC in 98. And what you see here is, of course, the omega and the phi are entirely dominated by the experimental resolution of about 6.5%. This will be improved by about a factor 3, which means that in that case, the omega and the phi peaks should be observable. So the first thing is, if we see this broad distribution and we say this is the melting of the rho, it would be gratifying to also see some sharp peaks where one would not expect the melting. Now, beyond this, there is, of course, an interesting physics question, and there's a long debate what happens to the phi and to the omega. And there are certainly striking predictions what happens to the omega, to the relatively small fraction that decays inside. But this is something we would like to see. The other thing is that for the phi to measure in the same experiment, the E plus, E minus, and the KK channel would be very interesting. There have been predictions because it is so, the decay momentum is so small. So if either the phi or the kaon mass changes, one can really expect a large change in the branching ratio. And this is something which you only have a chance if you measure it in the same experiment, I think.
Okay. Thank you very much. We will have a little break now. We expect you to be back at 10 past 11. Right?